Okay, so let's get started. Thanks for coming today, those of you who are here. So we're going to talk about anomaly detection today. Um, we'll this will be I guess a bit deviation into a bit more statistical modeling, just to give you a sense of how this can work. I'm myself fairly agnostic to a lot of the details of the statistical modeling, but I'll show you some calculations which I think really illustrate the point really well. And then I think you can swap out those with other statistics, and kind of the big picture will work well, hopefully. Yeah, let me also say homework 6A was posted, right? So here it'll be due in a week. So the homework 5 was due today. Hopefully pretty light. 6A I'm hoping is simpler than even what 5 was by itself. It's only worth half the points. The other half the points will be graph analysis homework due at the end of the semester. We'll be looking at kind of modeling anomalies similar to what we're looking at today in class. So after the lecture today, you should be able to kind of do this homework. These equations probably now look pretty mysterious, but I hope by the end of class, this way of calculating things will be much less mysterious. And then I'll ask you to kind of look for outliers, and but it should be pretty straightforward. If you look at this, at the data set, I don't know if it'll let me see it on the iPad. Okay, let's not try and do that. But the data says just like 100 values, so it's not very complicated. So it should be pretty. Hopefully, it's pretty straightforward and lets you kind of illustrate the points. Okay. So let's talk about our. So anomalies, and this can mean many different things. I'll try and give you kind of a fairly general and very well principled approach to doing this that I hope will kind of you'll be able to use your imagination on how to apply it lots of other scenarios. There are going to be 3 components that you need to think about when doing anomaly detection. Okay, and so these 3 components, I guess we can swap out with other things, but the first is what to expect from your data. Okay, so this is stated fairly generally, right? So what to expect from your data. Start. So it's intentionally stated pretty generally. So we are in the unsupervised realm here, right? So we're in the unsupervised. So we do not have labels on the data. So we can't kind of use labels to do prediction and use how well we do prediction to kind of evaluate how well we're doing, which means that we have to kind of have some sort of way that in order to determine or tell if we think something is an anomaly, we have to say, well, what do we expect normal data to look like, right? So we have to write down some sort of model that we expect the normal data to look like. And so this requires modeling some knowledge, and I will give a very specific example, but hopefully by the end you kind of see that you could swap in something else. But this is a very data and task task specific kind of question you have to ask. And so if you remember from your data collection report, you were supposed to think about the data you used, what would be kind of a distribution that you could assume your data was generated from, right? So we'll assume that data is generated maybe IID from some sort of distribution, and we're making observations from this distribution, right? This is kind of a common way to think about this kind of, it doesn't have to be this way where we're assuming every data point is ID from a distribution, and we'll see kind of how stuff can deviate from this. But you have to have some model of what you think your data looks like to say what would be unusual in that data. What is an unusual chunk of this data, which would be like the anomaly in the data. Okay. So the second point is how what you observe can is allowed to differ from you, right? So from the distribution of your data or from what you expect. This is similar to, or you could think of this as the shape of the anomaly. All right, so I want to somehow define what could the anomalous region be. So I'm going to think about, so if we have an anomaly, we're going to think we're going to have a data X, and then the anomaly will be a subset of X. Okay, so we're going to think of that. We're going to measure. I will distinguish between when I talk about like an outlier as kind of a single data point, which is observed in some way, which is very different from everything else. Maybe this was a spurious reading like we talked about on Monday's lecture, where an anomaly will be a subset of the data. Okay, and so if it was just one data point, you'd probably say this is an outlier. But if it's a cohesive set of data that does not fit your expectations, then this would be an anomaly. Okay, and so then we don't want to say, okay, it's just this set of scattered outliers. We want to say the anomalies are kind of, they're all correlated in some way together. We somehow need to measure the shape of this data. So for instance, if you have data that looks like this, and there are a few points out here, maybe this is the anomaly, and these are like the normal data. These came from the distribution, and these came from something else. Yeah. 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 So those that's like a tricky case. Yeah. So those are kind of the hardest class. It turns out individual outliers are much easier to find or don't matter. They aren't really outliers. But so you could define an anomaly where this region is shifted over here, but it changes the distribution. Now, I don't necessarily, to find the anomaly, I could say, well, there's a normal shape distribution here, but then there's a jump in it. This might be easier to see in a one-dimensional example. So let's say I have data that looks like this, and there's a distribution of the data that looks like a normal distribution, but there are a lot of points right here. So the distribution kind of looks like this, so that there is some normal shape, mu, and then there's some anomaly here. Now, the issue is I don't necessarily need to know which of the points here are actually anomalous, but I know something is different from what I expected this normal distribution in this region here. So an outlier would kind of need me to say, okay, I'm going to select which points were the outlier points. Or the anomaly says, well, there's something going on in this region. Okay. And so that's why this kind of this idea of the shape of the anomaly, what does it mean to be, what kind of, if I have a couple of points here and here and here that all seem to be not matching the distribution, but they're not cohesive or they're not connected in some way, that seems stranger to think of as an anomaly, where this is a group of points altogether in some sense. In this case, a one-dimensional interval that where the distribution is much higher than I would expect from all the rest of the data. And so that's what I mean by the shape of the anomaly. Okay. In this case, it can be an interval in one dimension, kind of makes sense. We'll look at even simpler model for most of the lecture. Here, I just said, okay, it's a rectangle of points. Okay, this can take different form. I'm mostly drawing these two-dimensional examples, but you could, or one-dimensional examples, but you could imagine this. Higher dimensions is more challenging. You can imagine this with graph data or with text data, where you have some, there's some block of text that all of a sudden has a bunch of swear words in it, right? Okay, maybe that's anomalous from like standard articles in like Wikipedia or the New York Times. So, but like, why is it that set of articles as opposed to if they're scattered all over the place, maybe that's not anomalous, that's just part of the distribution. So you want them to somehow be cohesive in some way. Okay, so you somehow need to think about how you measure what subsets could be the anomaly. This is how we're defining it in this class. There's probably like 30 different ways you can use the word anomaly, but this, I think, will give you an important class of tools to use. Okay, and then you can, so then the last part is, and this part also has to do with some algorithms. I'm going to have to then find this shape. So I'm going to have to think about the algorithms in the second part. Okay. The third part will be to determine if the most anomalous kind of subset S found is interesting or not. Okay, so for any data set I have, even if it just looked like the green data set or just the part inside the red circle here, I can always define what I would expect, run an algorithm that finds the most anomalous region, and then I can report, here's the most anomalous region. It doesn't mean there's actually something interesting going on. I need to somehow evaluate, was what I found actually interesting or not? Was that actually unexpected or not? This was the most unexpected subset. That's always true, right? So, but it doesn't mean that it's actually likely to be an unexpected kind of subset of the data. So we need to quantify, was this unusual or interesting or not? Okay, and so that's kind of the last part here. Okay, so you need these kind of three components, and I hope these will become clear through kind of a longer case study in this lecture, and then you will kind of review it in the homework. Okay. Great. So let's start what to expect from data. So number one, what to expect from data. And so we're going to work with a kind of a model where we're going to assume X x1, x2, up to xn. And these are IID from some, let's say, distribution mu, and it's going to have a parameter. Okay, so it might be multiple parameters, but we're going to work in a parameterized settings. There's like non-parametric ways of doing of statistics. Non-parametric ways means that you actually, it's not that you don't have parameters, you just have like way too many parameters to kind of think of them individually. But we're going to think of having a small number of parameters, okay? And most examples of one parameter. And so what we're going to do is to define the likelihood. Okay, we're going to call this L of X, given that we have a distribution. We assume it comes from some sort of distribution. I'm going to define a function for a likelihood. Okay, and if you have data, do you want the likelihood to be larger or smaller? Yeah, you want it to be larger, you want it to be more likely. These names, and I try and use names like distance and similarity and likelihood in ways, and they're usually used that way, in ways that make sense with the English meaning of the word. So you want something to be more likely, right? So this is what the likelihood it's got. And we'll kind of derive a version from statistics. Okay, and we will write Lx actually without the parameter as the arg, actually as just the max over the choice of the parameter of okay, this would be the maximum likelihood kind of, and if I took the argmax, so I returned the parameters, that would give me the maximum likelihood model of the data. So how do we think of, and then our goal is to define, yeah, so let's, and then the goal is to define or find define, I couldn't decide. Okay, define a subset S of X. And so this will be a nice subset that's in a shape that we'll kind of get to later, where we're going to compare the likelihood of S, okay, times the likelihood of S or of X set minus S. And we're going to look at that divided by the likelihood of X. Okay, so again, these are the maximum likelihood under the family of models we're going to consider. And the idea is if I consider a subset, I can fit a model that kind of is representing this data better than if I fit one big model. I can fit a smaller model here, another smaller model on everything outside of my anomalous subset, and look at the ratio over these two likelihoods. This is called the likelihood ratio. Okay, and so we're going to define an example of this, derive the likelihood and probabilistically kind of using a statistical model, but this kind of way of comparing it is a pretty standard way of doing it. So this would be the likelihood ratio, okay? And you want to say that the model, when you fit the likelihood with the subset, the anomalous subset, and everything else separately, then everything together, then this ratio is large. I get a much more likely input model when I separate these two things. And so this, if likelihood is better when it's larger, I should always be able to do Okay, I need one more thing to be able to explain this. I'm going to assume, yeah, so I had to remember I assumed my data was IID here. Okay. So then the likelihood was going to be a product. The likelihood of the data is going to be the product over xi in the set X of the likelihood of xi given this data. It's the product of all of the data here, right? So I'm taking the likelihood of each data point and I take the product of all these things together. That means I can split up the data into two parts, S and everything outside of S. Okay. And I'm taking the product. This is a product and this is a product with different terms in it. So it makes sense to split these up with a product and not by a sum. Okay. This comes from the IID assumption that then the likelihood is independent for each of the observations. And so then I can total the total likelihood by taking the product of all the likelihoods of the individual pieces. So that's why I can decompose this into by a product instead of a sum or something else. All right, so let's go through a concrete example here. Okay, let's assume that my model is going to be a normal noise with some parameter p and some standard deviation. And I'm going to assume that that sigma is known. Okay. So when I say normal noise, often there's a mean and then there's a standard deviation or a variance. And I'm going to assume the variance is known. If I don't assume it's known, it's going to cancel out for most of it. So it's not going to be too important. Okay. So then if this is the case, and this, remember, is equal to 1 over square root 2 pi times sigma times x of the difference between p. So then the likelihood of xi, or I can actually say even better, I can say the probability of xi given this model is equal to xi squared divided by 2 sigma squared. Okay, and we're going to set now theta is equal to this value p. Okay, so I can is this value p, which is the center of the normal distribution. Okay, so this is the probability of an individual point if it comes from this distribution. This is just the normal equation for the normal distribution. Okay, and so then I can write down that the probability of x, the full data set, and I'll just write p here, is going to be the product over xi, because these x are again, because the x are independent of the probability of xi given p, and this is equal to the product of xi and x of 1 over 2 pi sigma xi minus p squared to sigma squared. Okay. Now I can write down the full probability of x. So when we write down a likelihood, we often say we don't care about certain factors, and we'll say that this is proportional to Okay, so this term here got dropped because it's the same no matter the choice of the parameter P or what's in the data, X. It just depends on the number of pieces in the data. So I can say this is proportional to, this is kind of proportional to here. And I would often call this term the likelihood of x given P. Okay, so the likelihood is often written, you may not have the proper normalization term, so it may be off by a constant factor, and so that's fine. You often ignore these terms in the likelihood, and this will be good. It will simplify the equations. Okay. Okay, I just care about the larger the better. And remember, I'm going to put this in a ratio, right? And this constant factors in front that are consistent are going to cancel out in this ratio. Okay, so everything will be fine if I don't worry about those things. All right. Okay, let me copy this here. Okay, so I'm going to use this term, and I want to talk about instead what'll be nicer to talk about is the log likelihood. Okay, and what it's going to mean is I'm going to take the likelihood, and I'm going to take, in this case, the natural log of the likelihood of x. Okay, and I brought this back to remember this equation I have here. Okay, so now I can write the log likelihood of x given P. Okay, so this will be the log of the product of xi and x of xi minus P squared over 2 sigma squared. Okay, and so there's going to be some really cool simplifications that will happen here. And if you've taken the foundation of data analysis class, hopefully you've seen something similar to this before. But I can push the log through the product, and out pops the sum. Oh, and there was a minus sign in there. Okay, and then the next step is I use the natural log because it's going to cancel with the x. So what's going to come out of here is I'm going to get negative xi minus P squared divided by 2 pi squared, right? So this will equal negative 1 over 2 sigma squared times okay. So the log likelihood of this model is going to get out 1 over 2 sigma squared and times the sum of the squared distances from P. And I mentioned before, right, that I wanted to find the maximum likelihood model. The maximum likelihood, this is what I actually want to work with. I want to say, if I have this family of models, what's the best fit I can have? Well, now it's easier to think of. It started, I hope, seemingly kind of complicated, but I've reduced the log likelihood down to this. And now I want to find the maximum. The log is a monotone transform, right? And so I still want to find the maximum of the log likelihood, which is now the maximum of the negative of some constant times the sum of the squared distances. And so now I can observe that the arg max of P of negative L, or of the log likelihood of P, this is equal to the arg min of P of the negative log likelihood of X. And this is equal to the arg min of P of the sum of xi minus P squared, right? So I dropped the coefficient here and the minus sign by turning the max to a min. And the point that minimizes the sum of the squared distances, this is going to be equal to P bar equals 1 over the size of X of xi, right? Is just the average, right? So if I take the average, this is the maximum likelihood estimate of this model. Okay. So the maximum likelihood estimator of the parameter P for the simple model where the data comes IID from normal distribution is going to be the of a data set we've collected is going to be the mean of the data set. And this is the P, in fact, is the mean of the normal distribution. So hopefully this kind of is not surprising. Okay, but this is kind of a concrete way of defining this likelihood and this maximum likelihood. And now we can go, now next step is we're going to go and kind of plug it into this likelihood ratio. Everyone on board so far? Have people seen this sort of calculation before, where with the negative log likelihood, or this is kind of fresh and you're seeing this? Okay, so these equations, they're in the notes, kind of review them. This kind of trick, I think, really helps explain why, if you haven't seen it before, one of the main reasons we study sum of squared distances. One is the algorithms are nice. Two is it corresponds with this maximum likelihood estimator when we assume normal IID noise on the data. Great. So okay. So now we can say that if we have X IID from a normal distribution, P sigma, okay, and then the likelihood of X kind of from this normal is something we described on the previous page, and L of X, right, which is equal to the arg max of, or is equal to the max of P in real numbers of L of X. Okay, this is true where we set P equals so the arg max is actually equal to P bar, which is equal to 1 over n of these xi, right? So we can define this model by going back and looking at the likelihood, which was this product of all of the of all these exponentials, but we're going to plug back in the average of all the points we've seen so far is this parameter, and we can write down that equation again. We won't actually have to write down that equation to look at it, because we'll see we can use the sum of the squared errors. What we want to look at now is the likelihood ratio, which remember is L of S times L of X set minus S divided by L of X. Okay, now these, remember, have chosen the optimal parameter inside of them. This is the likelihood of the best fit model if we fit everything with one model, and this is if we fit a model for the stuff in the anomaly, and this is if we do it for the fit stuff outside the anomaly, right? So this is now equal to of of S, where this is P bar of S times the likelihood of X minus S, everything outside the anomaly, times P bar of X minus S, divided by the likelihood of X with parameter P bar for everything. Okay, so now I can write down this equation directly. I can solve, there's a closed form solution for what is the optimal, the maximum likelihood parameter. I can plug this in and I get this likelihood ratio. But again, I don't want to calculate this. It is a product of a bunch of exponentials and it's messy to calculate. So why don't I use the log again? So what people typically write down is the log likelihood ratio, and that's the natural log of L of X minus S. Okay, and so when I do the log, I can push this through. This is equal to the natural log of L of S plus the natural log of L of X minus S minus the natural log of L of X. Okay, if you remember, the natural log of these was just the sum of the squared errors. So now I'm adding the sum of the squared errors fit in the anomaly, the sum of the squared errors fit outside the anomaly, minus the sum of the squared errors fit universally on everything. Okay, so let's draw a picture now. So we're going to assume that we have data where this is x1, x2, up to xn. And we assume this data is going to come on a fly here. And each data point, so this is x1, this is x2, x3, and it's kind of noisy here. So I have data points coming on the line. They probably actually, let's say instead, these are actually points. So I'm going to say this is x1, x2, x3, x4, and then there's, at some point it changes, perhaps like this, right? So this is x7, this is x8, x9, and so forth up to x30. Okay, so there are some values here. And if I fit everything by a mean, this axis will be the value here, and this will be the mean of everything, of all of the data. This line will be the mean of P in the subset. Let's say there's some subset S, right? And so then this subset here, this is X set minus S, and I will fit the mean of all of this data here as well. Okay, so then my error is going to be the sum of the squared errors. And so either I can measure the errors like this up to this mean, right? So this is the default measurement onto this mean. I look at the sum of the squared of these residuals, or I can do something where I measure the distances to the means fit inside and outside these regions, right? And the hope is that, right, that the sum of the squared error bars in these are much less than if I have just fit one error to everything. Then I would say if these are much different, I could say this is possibly an anomaly maybe this sequence goes much further, and there's one region where the error seems to be different. Okay, and so this, the region S, the most anomalous cell region S is the one is, so let's define this as LLRS of SX, right? That is equals the arg max of the region LLRS, the log likelihood ratio with respect to S and X. Okay, so I can define this function, log likelihood ratio. It could have been the likelihood ratio that would work fine. It gives me the same maximum, but it's easier to work with when the logs cancel my exponents. Okay, to find the region S that maximizes this log likelihood ratio. Okay, and maybe you see in this picture that this region, all these points are much lower, and then the blue points are much higher. I kind of color-coded them so you could see it more easily. But if you're just given the data, you don't know which ones are maybe anomalous and maybe not anomalous here. And so this would be one way of kind of trying to look at this. Okay. Okay, so we'd like to find the region that maximizes this log likelihood ratio score. Okay, is this the best possible region to find this subset here? It probably is here, but let me draw a different. Let me again take a snapshot of this. Oh. Okay, well, let me draw a different picture here. So maybe it's less obvious where we should pick S, right? So let's say all right. Can you see all the dots? Are they large enough to see here? So where is the best region to pick S now? And kind of think of a couple ways to try and do it. I could choose this subset of points. Why don't I pick these points as S? And then I can fit for all their other points. So I can fit a model through these, and then I can fit the red line through the rest of the points. This probably minimizes the sum of the squared errors here. Okay, so is this the good set for the like the anomalies? The other option instead of this would be to say that this region would be S, and then I have to fit the baseline, everything else is here, and then I have to fit error like all right, and then in S, okay, so maybe we'll call this one S prime. All right, so with this data, maybe there are two possible ways that might make sense to define S. Which one do you think is the right way to do this? The green one will probably give a smaller score here. Okay, so let's say the green one gives a smaller log likelihood ratio or a larger log likelihood ratio score. So you think that's the right way to find the anomaly, or should I use S prime? This one, the score is maybe almost as high, but not quite as high. You think which one? S prime? You think S prime is more interesting? Yes. Okay. Well, and you think because
Maybe first of all, there's more
has more points in it. Okay.
closer together.
And they're closer together. Okay. So this one has more points and they're closer together. Okay. In fact, they're kind of consecutive here. And this one has a larger LLR score. Okay. So S has a larger LLR score. S prime has more points and they're closer together. Yeah. So who thinks, let's just do a vote to see what you think. There are no right or wrong answers. Who thinks S is probably the better choice of anomaly? Who thinks it's S prime? Okay, and okay, that was most people vote. And who didn't vote yet? Yeah, there are a few. Okay, few people. Okay, so yeah, so I think S prime is kind of is a more interesting anomaly in that it's kind of grouped together in this way. And I kind of alluded to that earlier in the lecture. That may not be the case. This one may be more interesting. It could be that these are happening on the days of the week, and every Sunday you have some different pattern happening here, and there's a regular pattern that's happening, and then maybe something happened this Sunday and it was skipped, or maybe I should have drawn another one of these data points here. So kind of this comes down to the modeling of what the shape of the anomaly you want this to be. Okay, what shape of the anomaly to so consider. Okay, so S prime is going to be an interval so subset. Okay, so it's an interval subset. It defines a nice kind of cohesive shape. Maybe these are observations in a time, and after some point, something changed, and this was lower, right? So maybe this is amount of like water used in people's houses, and this is their sprinklers are on a certain pattern, and then at some point it became fall, and we don't need to turn the sprinklers on, and then the amount of water was decreased. Right, so this is kind of there's some change point happening here. Maybe this is more interesting. You found that because there's an interval kind of subset here, but this is a modeling choice. What shape to use here? There might be another interesting pattern if I reconfigured it to be days of the week or something else. There might be another interesting pattern with the green ones that might also be an interesting subset. But you need to define this. Okay. So in order to, in finding anomalies, okay, what you need to do is to define a class of possible anomaly shapes. Okay, and shapes, it can mean what you want it to mean. So then you want to find the arg max S in some family of shapes that you consider of the log likelihood ratio score between S and X. Right, so I can define a cost function that was derived somehow from what I expect my data to look like. Right, so this tells me kind of what is derived from what I expect the data to look like, but then I need to define a class So a class of shapes, and that's what this script S is supposed to be, right? So there's some family of shapes. So these could be intervals in a time series. Maybe these are the days of the week. These could be kind of some spatial so regions, say defined by circles or so rectangles, or if you're doing machine learning, you might say some half spaces. Okay. Where the distributions look differently on one side than the other side of the half space. This would be, you can drive a linear classifier by considering spatial regions, and I have, you can define like logistic regression. If I have data that follows one property here and another property here, and then I have a half space, right, that says on this side of the half space, it's different than on this side. You can define like much of linear classifiers based on this model and so on. Okay, you don't use normal distribution for your data. You use some other like 0-1 distribution, and then you can, with some other things, you can define kind of the logistic regression or other common models of linear classifiers. Or if you have other families of shapes that you can define your classifier by, you can derive it this way as well. Okay. Okay. So you need to find a family of shapes. Okay. So to define an anomaly, then I would say S star, the most anomalous region, okay, is the argmax of this. I want to maximize the log likelihood ratio or some other function, right? I could define some other function that somehow says, if I have a large anomaly, if S is an anomaly with respect to my data set X, then this function should be large. Okay, I could define something else. I don't have to drive it as a log likelihood ratio. There's from statistics, this is going to give you kind of the most powerful sort of hypothesis test for certain things under a bunch of assumptions, but I could define a different kind of function here if I wanted to. And everything would still make sense. Okay. If I wanted to find some function, I want to maximize some family of shapes that maybe are going to do a good job of something is different happening in these subset than in everything else. Why do I care about restricting to the number to a family of shapes here? Why don't I just say, like, this could be anything? Well, why do I want to say, well, I want it to be an interval, or maybe it was some regular pattern, or there was something else here? Why don't I just consider any subset? Yeah. Yeah, you could, I think you could overfit here, right? So I think, yeah, so overfitting has become more of like a delicate word. Some people no longer believe in overfitting. I think it's still relevant in some cases, and this would be one case where you could do it, right? So if there are a bunch of incidents on a map, right? If I have a distribution in like, so let's say we're in Utah, and there's a bunch of instances of strikes of like lightning, okay? And then there were some of the lightnings caused some fire, okay? Let's say these lightnings caused a fire, okay? And so can I have my subset of X actually defined as this region of points? I say, aha, this region is the most anomalous because these caused a fire and these did not cause a fire, or the amount of fire that were caused by this. Last semester in this class, some people were analyzing spatial data where fires started, and they were in California instead of Utah, but they were kind of all over the map. So can I say that this subset is some anomalous regions that are interesting in some way? Well, just looking at the map, I would say this is not telling me anything useful about the data, right? If no restriction to class, right, some class of shapes, then does not provide useful understanding. Right, so if I don't understand what the subset could potentially mean, maybe there's some kind of spatial relation between them, or there's some physical phenomena based on the sort of terrain here, or I'm trying to predict where the next fire will start. I feel like I haven't learned anything by looking at this example with this sort of anomaly. Okay, I want to restrict to a family of cohesive subsets in some way. It doesn't have to be spatial. I could be looking at what the vegetation was, or maybe during the time of year, when was it really dry or was it not very dry, and looking at that sort of information to kind of define the classes of similar things in some way that would somehow be meaningful. So if I were to find an interesting subset that had a lot of that was very different from everything else, then that would potentially imply some useful, interesting pattern. Okay, but if I don't restrict this, then I'm not going to necessarily find some useful understanding. It doesn't mean there's a causal relationship here. I don't want to say that, but I'm more likely to find useful correlation if I restrict to a class of shape families which might encode interesting information. Right, so that's why we would like to kind of restrict it in this way. All right, so let's go back to our example. Okay, where x is x1, x2 up to xn, and these are real values. And I have something that the xi occurred somehow, that there's this other aspect, something like the time of xi occurred before the time of xi plus 1, right? So there's a time ordering sequence of these, right? So now, again, I'm drawing them, and I have, this is x1, x2, this is the real values, and then, these are occurring with some noise, and this is x12, x13 up to x30, right? So there's a sequence here, and they have some real values. And so now let's choose, I want to choose that my subsets are going to be the family of ST, such that ST equals the X is defined by the I less than equal to some value T. Okay, so that there's some value T. This is defining a subset. So these look like, I'm going to call these one-sided intervals. They're going to be like negative infinity up to some point T. So this will be S, and afterwards will be X set minus S. So I'll define my family of subsets to be these one-sided intervals. Okay. Okay, when I have the one-sided intervals, then I can try and solve. Now I can solve for S equals R max S in this family of the likelihood ratio of S X, right? So this could be XT. So I need to just choose this value T, this time point at which this switches. Okay, so this is called a change point model. Okay, where there's some sort of property that's happening up until time T, and then that property changes afterwards. So a lot of time series stuff like in like in econometrics, they like to say, okay, this stock price or this other quantity behaved like this up to some point, and then after that point, something happened there and caused the distribution to change. I'd like to determine this time point, right? And so that's kind of the goal here. And so that would be an anomalous region with respect to the whole region. I could define it as being a different sort of subset. It could be a subset interval that occurred in the middle. That will be harder. Now I need to choose two values. But the nice thing about the time point example, the change point example, is I can usually solve this one very efficiently. Right? I can find the optimal subset basically by scanning it. Okay, so now I can solve in usually O of n time. I can solve this in linear time by maintaining the log likelihood ratio of the score, my scoring function I'd like to make large, by fitting a model as I'm streaming through the data. I can maintain the mean of all the points here, and then with that mean, I can maintain the kind of the sum of squared variations from that mean. And this corresponds with streaming algorithms. These correspond with streaming kind of algorithms for the mean and the variance. So if I'm maintaining the mean and the variance, I can update it as I'm sliding along. I can first compute the mean of everything to get my denominator, which is fixed in the log likelihood ratio. And then I need to get the mean and in fact, the variance, the average deviation from the mean in the numerator, and then here. And so I'm adding 1 point at a time for the L of S, and removing 1 point at a time for the L of X minus S. Okay, and I can maintain this in a sweep in linear time over the data. Okay. Okay. If you're interested, we can go over that, but I think yeah, the details are an extension of stuff we talked about with streaming algorithms. This makes sense? So this is a nice model that I can solve the optimal anomalous subset very kind of I can do this very efficiently. So if this is T, then this set defines S of T, and then over here, this would be X set minus S of T in this region. Okay, so what if I have, let me just say one more thing. What if I now have some data? So this would be kind of some spatial data. And there are some values of some interesting of these. Maybe they have a larger value on them. Okay, and now I'd like to find a circular region. Let's not talk about circles. Circles are a lot more complicated. I'd like to find a rectangular region that has a lot more of the high valued points than the stuff in the background, right? I'd like to find, let's call this S, right? And so red, these have a high value. These have a low value. So I'd like to find this region S that's kind of an anomalous region here. There's a bunch more high value points in this rectangle. Okay, so how would I find equals the arg and these are all the rectangles of the log likelihood ratio. It's a little bit harder than the one-dimensional problem, right?
Rectangle or
Yeah, let's say it's, I can consider any possible rectangle as my region. So I can define the rectangle by 4 points here. Let's call this A1 and A2 and B1 and B2. I can define it by 4 coordinates, right? If I define the lower left corner and the upper right corner, maybe this is, right? This is the X coordinate. This is A1. This is B1. And then this is A2. And this is B2. Right? So I can define it by 4 parameters now. And I have to search this parameter space. So it's kind of tricky to do, but I can actually, well, let me first sort all of the data, the X data by their X and their Y coordinates. Okay, and then as long as the left endpoint doesn't change between which of the data point X coordinates is in between, it doesn't change which points are inside the rectangle. So I can sort all the points by X and Y, by X coordinate and Y coordinate, and then I can consider every choice of boundary for the left side and for the right side of the rectangle and the X coordinate and for the bottom side and the top side. And I can check all of these. Okay, so it's kind of slow, but this would allow me to search over all of these to find the one that maximizes the score.
this because you know which one is the high value, right? So you pick them first, then you just pick go through each of those and find the rectangle. And once you know all the point in the rectangle, you know the ratio between the rectangle and the whole data set, and then you can actually do it in linear time. After you short.
So for this model with the sum of the squared errors, I've a paper that's conditioned on some hard problem thought to be very hard that you basically need to spend at least quadratic time on it. You can get it down to, yeah, and we can get it down to basically quadratic time, but not end of the 4th time, but we can get down to n squared time, but you cannot do linear time. If you could do this, you would solve a major open problem in algorithms, it turns out. So I won't get into the details of this, but yeah, so this takes a bit longer to do. But you can actually scale this up to pretty large sizes. I'm not going to get into them in this class. It turns out if you have millions and millions of data points, if you randomly sample the data points, you can show you kind of preserve where the anomalies are if they are interesting anomalies. they're not interesting anomalies, then it's not important. And if they're interesting, that means there's a lot more high value points inside than outside, and you can find them on the sample. And so then you can run on the sample, and the sample is small enough that you can run in quadratic time, and it's not so bad. So and for spatial data, this is pretty doable. Circles is another story, because then how do I define all sets of circles? But it's not so bad either. All right, but the point is that you can define this family of shapes, right? So in this case, I have S rect as all rectangles. And by defining a family shape of rectangles, I can define the same problem. I can use some scoring function. It can be a log likelihood ratio or something else I want to put in there. And I can maximize over this. I can always find the most anomalous region in this one. This is basically how it should work, but you can plug in different families of shapes or different cost functions here. Okay. One more thing I want to talk about. I promised there were 3 parts to this. We got through the first 2 of them. How to define a cost function for what is likely, what is expected, or what is unexpected. How to define a family of shapes, and thinking a little bit about the algorithms. And the time series one with change point is a pretty simple one, and this is what you will play with in your homework. The third thing is, okay, how to quantify if the anomaly is interesting. Okay, I want to quantify if the anomaly is interesting or not. I can always run, when you're doing this, you write code to say, I'm going to scan over all choices of t, and for each of them, I'm going to compute a log likelihood ratio score, and I'm going to take the largest one. I'm going to find the t that gives me the largest score. That is my anomalous region. Okay, I found every time you run the code, you will find some anomalous region. So S star arg max, right? This always exists. You could always run code and it will always give you an answer. Okay, this is going to be some code you run. Okay, and it's going to output some answer, and it's always going to give you an answer. Okay, so now what? Should I go tell, my collaborator an interesting anomaly? It's this one, right? You should go and look at this. Something interesting is going on here. And so what we need to quantify, I found something, is it interesting? Okay. You found something, S star, is it interesting? Okay, so I'm going to give you kind of 3 ways of approaching this question that will kind of increase in the generality here. Okay. Okay, so option A, I'm going to trust the log likelihood ratio. Okay, we spend a bunch of times in this lecture, more than we have in other lectures in this class, actually deriving an actual statistical quantity. And okay, it's based on some IID normal assumption. We wrote down some equations and we said, okay, this is actually the log of the likelihood of the ratio between the likelihoods. I should be able to look at the ratio between the likelihoods and say if that's interesting or not. Okay, and so there's kind of some rules that the log likelihood ratio that is, say, greater than 10 or if you reverse it, is less than 0.1, that is kind of interesting. Okay, and these are approximate. Okay, and in fact, there's a way you can use this to directly drive something like a p-value, and I will say a little bit more about p-values even more in the next option. Okay, but if you trust the log likelihood ratio model and you see something, say, bigger than 10, or this is the log of it, actually the likelihood ratio. So I think the likelihood ratio it's the log of this, so it should be even smaller. I think it's bigger than like 2.5 and like 0.2, less than 0. So when the log likelihood ratio is, sometimes it should always be positive. The likelihood should always be larger for this model because I'm giving it more power to fit. But sometimes people will swap the two roles of these things and they'll put this guy in the numerator. So let me just say specifically this one. Okay, so if the log likelihood ratio is bigger than, say, roughly 2.3, 2.5, you can say this is pretty big. This is a big difference between the two options. Okay, the problem with this is that, well, if I'm allowed to fit a much fancier shape to it, I can probably fit the data much better. The more powerful I can the larger my family of shapes, the better the likelihood will look for the model that has the anomaly in it. Okay, so you have to be really careful about this. So if I make the family larger, then the log likelihood ratio will also go larger. Okay, so if you really trust your family of shapes of your anomalies is not too expansive and this is realistic what you're looking about, some people will directly use the log likelihood ratio. For the spatial statistics, the spatial anomalies I was talking about, there's a famous, well-known software called StatScan, which basically does this. It will give you, it will output a p-value and say, this data would have occurred less than 1 out of 1 billion chances or something like that. And I think those the numbers that come out there are not. I think they're over. They're kind of over optimistic about how well the modeling is here. Okay, so I don't trust this one as much, but there's a lot of work that does. And if you really trust your model, you can go for it. You can directly read off the log likelihood ratio and decide, if you think it's interesting. Okay, and definitely the larger the log likelihood ratio, so the more interesting the model, but you need to calibrate by the family of shapes and other things that go into the modeling. Okay, like what is your distribution? Option 2 is to resample. Okay, so I want to, I'm running out of time. Okay, so I assumed X was from some distribution. So if I know this distribution, then I'm going to generate, let's say, M more data sets. Okay, so X1, X2, up to Xm, all these are from the distribution. So if I assume I know what this distribution is, this is a total of M times N points. Okay. Now I'm going to run my algorithm. I'm going to get an Sj of arg max S in my model set, log likelihood ratio of S of Xj, and I'm going to get a score log likelihood ratio of Sj of Xj. And this will give me a set of these scores, gamma 1, gamma 2, up to gamma m. And this will form a distribution of these gammas, right? So I can think of there's some distribution of the gammas. And then I look at gamma star equals log likelihood ratio of my S star of my original data X. And I can say, where did it fall in the distribution of the gammas I sampled from what I thought was the model of my data? And I can look at the area under the curve, right? The fraction of things which are larger, the frac larger than gamma star, this is going to be my p-value. Okay, so if I rerun data, I said there's going to be some clustering just based on the randomness of the process. And if I can rerun it and I calculate a score, there's going to be some distribution of these scores. And I look where the one I found on the data I actually collected fell with respect to these. And if I look the fraction of the observations from the resampled data larger than my value, this will kind of give me a p-value. So if I run like 1,000 of these and less than 50 are larger than my score, then I say the p-value is less than 0.05 under this model that I assume the data came from. Okay, this is explicitly states your model of the data. And then it doesn't really matter what you use for the score of the algorithm, but as long as you think it's meaningful, you can generate a meaningful kind of p-value. And if it's less than 5% or less than 1%, you can reject the hypothesis that it actually came from that distribution. It somehow is different from this. And this is a well-founded approach, substituting just about anything in this algorithm here, as long as you think that's a meaningful way of describing what the analysis is. So I can define shapes and scores and a bunch of other ways, and this will work. Okay, let me just quickly say in one sentence, option C. If I don't know how to regenerate, I take the data set and I just permute the values on the data sets. And then I rerun this algorithm m times, and I do the same approach here. This is called a permutation test. I don't need to generate new data. I just take the sequence or the spatial location of the data and I reshuffle the values around and rerun my algorithm. And if I can find that my score is very unlikely, then I can still get some sort of p-value. And that's an even more general approach. All right, so we'll stop here. You'll get some chance to play with this in your homework.